All right, everybody, let's get started. I had mentioned this a little bit before class, but I'm very excited today because I'll give you some background. It has been probably about 7 years since I've covered this topic in this class. Marshall recently went from a 14-week semester to a 15-week semester, and so I now have time to cover this, and it's been. I'm really excited about it. What we're going to do today and for the rest of the semester is basically answer one question, which is how does masthand work? Okay, and what we're going to do is we're going to get a little bit of a peek into the background on how masthand works, and we're going to do it on what I'll say are very, very basic problems. So the whole taking a sledgehammer to an ant, analogy or whatnot, it's going to feel a little bit like that for the types of problems that we're dealing with. But the method that we're going to develop, I think you'll kind of see how this method could apply to really any structure of any complexity. I told you last time that, if you open up the textbook, there's oodles of different ways of computing deflections, but we only covered one method. And the reason I only covered it is because it is the most broadly applicable. It will apply to any structure of any type computing the deflection anywhere, okay? Well, there's oodles of ways to analyze indeterminate structures. And if I'm going to show you how to analyze an indeterminate structure, and I'm going to show you one method, the method that I'm going to show you is matrix analysis. And we're more specifically how computer programs analyze structures. And so whether it's simple programs like, I don't want to say simple, but we'll say simple analyses like linear elastic analyses of 1D structures that you'll find in masthand or RISA or STAT or things like that, up to some really fancy stuff that you can do with Abacus or ANSYS or things like that. They all sort of operate off the same principles. So if you hear the term finite element analysis, how many of you have heard that term before? Okay, so this is kind of a flavor of how finite element analysis works. And so if there's any one thing I'm going to show you, it's going to be this. Okay, did everybody get the code? Let me say a couple quick housekeeping items before we move on to this. So a couple things. Project due Friday, Friday at 5 p.m. We're going to have lecture Monday and Wednesday. On Friday, I'm just going to be here to answer any questions that you have about the project, but we're not going to have a formal class on Friday. The other thing I'll mention, I have gotten a couple of housekeeping items here and there from some students about like a grade on this homework here and there. I didn't want you to think I had ignored you, but what I'm probably going to do is just deal with all of that next week, just to put a bow on everything. So I'm not ignoring you or anything. I promise. I'm just going to deal with it all at once, just so that I'm systematic. Okay, everybody get the code? Okay, all right, let's go through matrix analysis, okay? And a lot of what we're going to see here on these slides are stuff that we've seen in other presentations before, but I kind of want to think about it a little differently because when I first showed you this stuff, I was showing you it from the context of, I just want you to get an idea of how masthand works. Well, now we're actually going to do it by hand, okay? So I want to look at it a little differently. So I'm going to focus our coverage of matrix analysis in this class on bar element type problems. And so bar element type problems, I'm ultimately going to extend that to trusses, okay? And I'll maybe say a few things about beams and frames, but I'm going to limit our discussion on trusses. Over the next few lectures, I think you'll kind of understand why, but just for now, just bear with me on that. So let's go back to a basic mechanics problem of a bar being yanked on by some force F, and it elongates some amount delta, okay? So we have our undeformed length L, and then how much it stretches delta. We can compute delta as FL over EA, right? The force times the undeformed length divided by EA. E is the Young's modulus, A is the cross-sectional area. Everybody should be okay with that, right? Okay, and what we can do is we can take this and we can rewrite it a little bit. We can say, well, instead of looking at L over EA equals delta, what I'm going to do is say that EA over L times delta equals F. Or I'm going to say that K delta equals F. Okay? So basically what I'm going to do is I'm going to sort of translate it into a problem that you might remember from physics, right? You probably did a problem like this in physics where you had a force applied to some spring, and the spring had a spring constant K, and you could determine how much it stretches X as F equals Kx. Everybody should have done a problem like that in physics before, am I right? Okay, all right, so my point is that if you look at a truss, okay, a truss is just a bunch of bars, okay? So the idea is that we have fully formulated and fully solved a single bar element, while a truss is just an assemblage of bars. And I'm using this term very carefully, this term assemblage. You're going to see why here in a bit, because when we perform matrix analysis, one of the things that we're going to need to do is assemble a stiffness matrix, okay? So specifically what we're going to try and do is we're going to try and describe this system like this, okay? So instead of a stiffness term times displacement term equals a force term, we're going to say a stiffness matrix times a displacement vector equals a force vector, okay? And so the idea is we're going to write this in matrix format because computers do a really good job at solving matrices, okay? They are really, really, they're really good at it. They can do it very quickly. Humans, when you start getting into like 4x4, 5x5, 6x6 systems, you know, really big ones, it is really burdensome to solve matrices by hand, but computers can do it all day, every day, no problem, okay? So that's what we're going to take advantage of, okay? The other thing about this method is we're going to be able to define a single method that is applicable to any structure across the board, okay? And so let's talk about that method, okay? Now this you have seen before, okay? We've looked at this slide before. This is the flow chart for matrix analysis. And what we looked at it before, we looked at it from a masthead standpoint. And we said, okay, when you're running masthead, what you have to do is you have to pre-process the model, right? That means create the geometry, create the boundary conditions, create the loads, put the materials, the section properties on it, and then you click that little analyze button. And then when you click the little analyze button, masthead just sort of does something and boom, there's all the answers, right? That's basically how we treated masthead up until now, right? And if you remember, I showed you like a bunch of stuff, and I said, oh, don't worry about it, masthead's just doing this in the background. Well, now we're going to talk about what masthead's doing in the background. So the first thing that it does, and I've got this here, we're going to do this in steps. The first step is going to be it assembles the K matrix. And so the K matrix is basically like the spring matrix, if you will, for the whole system, okay? And so the specific way that that works is what we do is we take what we'll call here, let me write it like this. We write a little spring matrix for each member, for each element in the system, and then we have this process called assembly where we turn that into a K matrix for the whole system, okay? And one of the things you might notice is it looks like I might be somewhat peculiar in how I'm writing these Ks, like I'm writing sort of like a little k and a big K, and I'm doing that for a reason. Whenever I do these calculations, what I'm basically going to do is say that anything that's represented with a lowercase letter refers to an element by element response or an element by element answer, whereas anything that's written with a big letter, it corresponds to the whole structure, okay? So you can think of this lowercase to uppercase notation as sort of representing this assembly phenomenon, okay? But we'll get to that, how we do that here in a bit, okay? So the next thing that we're going to do is we're going to assemble what we're going to call the force vector, right? So you can sort of see where this is going. Like if we go back to our basic formulation, we're going to start off with the K matrix, then we're going to start off with the force vector, okay? And what I'll tell you is that for bars and trusses, this is by observation. and I mean this when I say this, this part is really easy, okay? The only reason that I sort of mention it as a completely separate piece of the process is that for bars and trusses, this is easy. For beams and frames, there is a little bit of work to do with assembling this force vector, but for us, we're not going to have to worry about it, okay? So you can probably see where this is going, like if step 1 is the K matrix and step 2 is the force vector, step 3 is going to be this, right? Step 3 is going to be the displacements. And so step 3 is going to be solving for the unknown displacements. So solving for unknown displacements. Okay? And I'm going to show you how we're going to do that. And my notation isn't really going to make sense right now, but bear with me, it will. We're going to take the displacements, which I'm calling these displacements as delta sub r. You'll understand why here in a bit. What we're going to do is we're going to take our K matrix, which has been reduced. We're going to invert it and multiply it by the force vector, which has also been reduced. Okay? And then the last step is going to be computing final results. Okay? And so the final results, here what I'll do is I'll put like a bullet here so that we can all sort of follow along what I'm doing. So this is a bullet, bullet, bullet. For our final results, we're really going to be focused on two things. We're going to be focused on reactions, and we're going to be focused on element forces. And don't worry, I know I'm throwing a lot at you right now, but you're going to see how this is actually pretty systematic and pretty step-by-step. Now, this is what Mastan did when you click the little Analyze button. Past this, you just sort of report the answer to the user, right? And so the user just puts the answer in a nice little pretty format fashion, okay? And so that's really what, like when we were running Mastan, we didn't really care about these gray boxes. We just sort of did this, hit a button, and got the answer. Now we're going to talk about how to get that answer, okay? Does that make sense? Okay. All right, I'm actually going to pass this out. I have a handout, and this handout actually describes everything that you have here on the board and everything you have here in this flow chart in a little bit of a little bit more of a sort of procedural step-by-step fashion. So I think that's enough right there. If you have extras, let me know. There's that. Okay, and again, there's a lot of stuff here on the slides, which are on the handout, which I'm just sort of giving you. Don't worry, we're gonna derive all this here in a bit. Okay. Now, in order to do matrix analysis, we're gonna have to do some matrix algebra. Okay. So I'm gonna take a step back and thank you. I'm going to take a step back and let's go through some matrix algebra, okay? Now, I want to be clear and I want everybody to sort of look right here when I say this matrix algebra, we're going to be able to use Excel, okay? So I don't want you to think that you're going to have to do a lot of this stuff by hand, okay? But what you're going to see over the next few slides is mainly just to sort of refresh your memory. So again, to be 100% crystal clear, you are not going to have to do this by hand. You are either going to be able to do this by Excel or you're going to be able to do this using your calculator. And you're like, well, what do you mean your calculator? We've already done problems like this before. Remember when we were solving 2x2 joints and we were saying, okay, we can take a system of equations and write it like this because a calculator can solve it very well, okay? Well, that's basically what we're going to be doing here. So computers love using matrix algebra because they can do calculations really fast. But in order for us to all be speaking the same language, I want to have a very quick review of matrix algebra. So I want to talk about what matrices are, how we can perform some basic operations to them, and then we'll have a little bit of discussion on what an inverse matrix is. Okay, so let's talk about matrices and let's talk about vectors. Okay, so first off, if I throw the term matrix at you, y'all generally know what I'm talking about, right? That a matrix is just a table of numbers, right? It's just a table of numbers that consists of m rows and n columns, right? So if I was looking at some arbitrary term in the matrix, like for example, A21, it's in the second row, first column. So term M2 is in the M row in the second column, right? So whenever you see the term like AIJ, okay? So for example, let's just like make up a matrix. Let's call this matrix, I don't know, C, right? And so matrix C would be 3 by 5, right? Because it has 3 rows and it has 5 columns. And if I wanted to reference, for example, term 24, C24, I would go to the second row, 1, 2, 1, 2, 3, 4, and that term would be 7, right? So term C24 would be 7. And I'm just throwing this notation at you because I don't want to throw this stuff at you later. You're like, wait, what does this mean? What is this? Where are you getting all these terms? I just want this stuff to be pretty familiar. So far, so good? Okay. Now, when we perform structural analysis, so if you ever take a math course in linear algebra or something like that, I mean, you're just looking at any type of matrix and trying to assess them. When we perform structural analysis, we're really only dealing with 2 types of matrices, most common. We're dealing with square matrices, so ones where you have the same number of rows and columns, and then we're also dealing with matrices that only have 1 column, okay? And so when I use the term vector, what I'm saying is a vector is a matrix that only has 1 column, okay? So for example, this is a 4 by 4 matrix. This is a 5 by 1 vector. Now, one of the things that's worth mentioning is that when you write this stuff on a slide or in a textbook, you'll typically refer to matrices and vectors with bold symbols, but it's kind of hard to do that by hand. So what you'll do by hand is you'll say matrices are surrounded by square brackets and then vectors are surrounded by curly brackets or curly braces. So if you're wondering like why my notation was the way it was, that's just me trying to say, okay, this is a vector, this is a matrix, this is a vector, and so on and so forth. Okay, that's just my way of doing it by hand. So far, so good? All right, any questions so far? Okay, all right. The most fundamental matrix operation that you learn how to do in a matrix algebra class is what's called a linear combination. And a linear combination is basically if I've got 2 vectors or 2 matrices, A and B, a linear combination would be adding those matrices up or multiplying them by a number, okay? Or doing both at the same time. So like subtraction is just adding 2 matrices up where one of them's been multiplied by -1, right? So that's all that is, okay? So if you want to add 2 matrices, adding 2 matrices is just done on an element-wise basis. So what you would do is you'd say, okay, if I have matrices A and B, and I want to add those 2 matrices, what I would do is I would just say, okay, this plus this, this plus this, this plus this, this plus this. Just match up each of the terms and add them up one by one. So this is definitely something you could do in Excel like with no problem, right? Everybody okay with that? So if I wanted to add matrices A and B, I would get, okay, -7, 7, 6, 7, 14, 3. You see what I'm doing? Just adding up term by term. And then if you wanted to do a scalar multiplication would just be done on an element by element basis. So if I wanted to do 3 times A, I would just say 3, 12, -9, 0, 24, 6. Just do that. Just each term times the number, okay? I'm hoping this is simple, right? Everybody okay with this? Okay. Now what about multiplying matrices? Multiplying matrices is a little more tricky, okay? The only way that you can multiply 2 matrices is if they are dimensionally congruent, okay? And that's just a really fancy way of saying that if I try and multiply matrix A times matrix B, if matrix A is m by n and matrix B is n by p, these 2 numbers have to be the same number, okay? Because the reason why is because if you want to obtain some arbitrary term in matrix C, the way that you do that is it's just a sum of products, and you have to sum over, from k equals 1 to n, so you have to have the same term here. Now, you all probably I'm guessing the way that you learned it is you would do like a row times a column, row times a column, row times a column. How many of you have seen it done this way? Is there anybody here that's seen it done this way? If you haven't, I'm going to show you. This is the way that I like to do it. I actually didn't learn how to do matrix multiplication this way until I was in an engineering course. I never saw a math professor show me how to do this. It was an engineering professor that showed me how to do it. The only other thing I want to mention before I show you this is that in general, matrix multiplication is not commutative, okay? And that's just a fancy way of saying that in general, A times B does not equal B times A. You can't reverse the order on matrix multiplication like you can with numbers. Now there is one very special exception to that, and that is that when B is the inverse of A, okay? But we'll get to that here in a bit, okay? So let me show you how I multiply matrices, okay? So watch this. So let's consider matrices A and B. So I've got matrix A and matrix B, so let me show you how I multiply them, okay? So the first thing I do is I take, if it's A times B, I take A and I stick it on the left, and I take B and I stick it on top, okay? And so the idea is that the answer goes in here, okay? So the first thing is that doing it this way, it'll help you figure out the size of the answer, right? Because you got to have, okay, 1, 2, 3 rows, 1, 2 columns. So that's how big this is going to be, okay? And then I did a lot of work on the PowerPoint animations here, so watch this, okay? So if I want to evaluate this term, what I do is I say, okay, 4 times 2 is 8, 1 times 3 is 3, 8 plus 3 is 11. And then the next term is going to be, okay, this is 20, 18, 38. Anybody ever seen matrix multiplication this way? I'm just curious. Okay, I've got some people shaking their head yes, some people shaking their head no. So I kind of like that everybody kind of, if you've never seen this. I find this to be a very convenient way of doing matrix multiplication, but the idea is you just keep going with it, right? So you got 14, 2, 16. And then you've got, okay, 35, 12, 47. And then you've got 18, 0, 18. And then you've got 45, 0, 45. And so the solution is that, okay? Is there anybody here that is confused by this? Has anybody's mind got blown, haven't seen this the first time? No. Y'all aren't. Your minds don't get blown by matrix algebra like mine does. I'm just a dork. So, okay. Do I need to leave this up here for a sec? You want me to go back? Oh. Hold on. Take your time. Everybody good with this? Okay. Now, probably, so if you ever take a course in linear algebra, you cover a lot of stuff. I mean, you cover like determinants, and you cover like vector spaces and eigenvalues, and a lot of what you are doing is sort of housed around a very fundamental problem. Like when you first learned about a derivative, right? A derivative was trying to answer a very fundamental question. You have a curve, what's the slope of the tangent line? And the answer is the derivative. And you do all this stuff with the derivative, like product rules and chain rules and implicit differentiation, all this hullabaloo, but really it all, like the reason for it was, what's the slope of the tangent line? Well, a lot of the motivating questions and things that you do in linear algebra is housed around, does a matrix have an inverse? Like, is there an inverse for a matrix, okay? And so I would say that the most important aspect about a square matrix is it invertible, okay? And invertibility is basically saying that if you have some matrix A, that there is some paired matrix, you know, some soulmate matrix B, such that A times B or B times A equals the identity matrix, okay? And what is the identity matrix? The identity matrix looks like this. I drew a 4x4 identity matrix, but an identity matrix could be 57 by 57, it could be 3 by 3, it could be 1 by 1. And an identity matrix is one where you have ones along what I'll call the main diagonal and zeros everywhere else. And you can think of the identity matrix as 1 when it comes to multiplication. So for example, what is 6 times 1? 6, right? What is 47 times 1? 47. What is 1 times 9? 9, right? So the idea behind the identity is that you can multiply the identity on the other side and it doesn't change anything. So you can think of like, if this is A, then B is its inverse if A times A inverse or A inverse times A results in the identity. Excel can do this. Computing inverses is really computationally expensive, and I don't expect anybody here to do it by hand. Your calculator can do a 2x2 or a 3x3. Pass this, break out the software. And I'm not going to turn this into a class on linear algebra, but I will tell you that the ultimate goal with what we're doing here is to get these displacements. And there are other ways of getting the displacements without inverting the matrix. But this isn't a course in Engineering 335 or matrix algebra. So I'm just mentioning that for the sake of completion. Okay. Let me take a step back. Is everything I've talked about so far, does that make sense? Okay. Now, I am going to add to this discussion on matrix algebra a little bit over the next few lectures. Like we're going to talk about what does it mean for a matrix to be symmetric. We're going to talk about what it means for a matrix to be orthogonal. But we'll get to that later. Today, we don't need that stuff. Okay? This is all we need for today. Okay. So, I want to talk about matrix analysis, and we are going to start with what I am going to call one-dimensional bar analyses. Okay? And so what do I mean by a one-dimensional bar analysis? Okay? The problems that I'm talking about with one-dimensional bar analyses are like this. Okay? Now this probably looks kind of scary. It's really not. Okay? What I'm going to be talking about is, let's say I have a bar. Well, I'll draw 2. We'll call this a spring, and then we'll say here's a bar. Okay? Now the reason that I'm calling this a one-dimensional bar element, okay, is I want to talk a little bit about what the goal is in a matrix analysis. So the goal in a matrix analysis is to directly compute what I will call the nodal displacements. Okay? So the idea is, let's say here's the spring, okay? This spring, after I apply loads and after I solve the structure, what I propose is that this node, this joint, deflects some, and this joint deflects some. And so maybe what I'll call it delta 1, delta 2, okay? In matrix analysis, what you do is you directly compute the nodal displacements, and then everywhere in between you interpolate. So really all that matters to fully define the answer is what's going on at the joints, okay? And so I'm calling this a nodal displacement, I'm calling this a 1D problem because I'm assuming for each joint that there is only one displacement, okay? And I'm only talking about displacements in the x direction. So while this probably looks scary, I think what you're going to find is that this is actually a lot easier than you would think. And this and this problem really aren't that much different. Okay? Now, whether we're dealing with a spring that has some spring constant K, or we're dealing with a bar that has some length L, and this has some E and some A, the problem's going to be handled the same way. Okay? Does that make sense? Okay. All right. So I'm going to start throwing the term out, degree of freedom. Okay. So a degree of freedom, okay, a degree of freedom is how many joint displacements there are. Okay. So both the bar and the spring have 1 per node. Okay, per joint, okay? And so my goal in this derivation is to figure out this, okay? I think I put the E on the outside, doesn't matter, okay? So what I'm trying to figure out is what is this stiffness matrix. So maybe what we'll do is we'll write it like this. And this is really what I'm trying to figure out. This is my goal. Now you all are sitting here looking at a sheet of paper that tells you what the answer is. I mean, it's right there in front of you. But I want to see if we can figure it out together as to what this spring matrix is. Okay. Make sense? Are we okay with this? Okay. All right. Now, let's go through some ground rules before I get to this derivation. Okay? Now, this slide, you've seen this slide before. There's nothing on this slide that hasn't been in an earlier presentation, but I'm representing it from a different perspective. Okay? So the first thing is that I told you that we're going to start interchanging the term joint and node and the term member and element. Right? Remember we started doing that with mass hand? Well, I'm going to start using that terminology here. So what I'm writing here, this case of E here, or this case of E here, is a spring matrix for the elements. Okay? Units. Okay? Everything I'm about to do is blind to units. Okay? Everything has got to be in a consistent unit system. Okay? So we will typically perform our analyses in kips and inches. So whenever you look at a problem, you better convert right off the bat. Okay? Now what about sign convention? Okay? This is really important. Okay? We need to refer to all of our quantities consistently. And so what's going to matter for us, since right now we're only dealing with 1D structures, is this x direction. So anything that's to the right, any nodal force that's to the right is positive. Any nodal displacement that's to the right is positive. Okay? So notice how on the board when I drew this bar and I drew this spring, I'm showing a delta 1, delta 2, I'm drawing it to the right because I'm sort of saying that would be positive displacement. Okay? Does that make sense? Okay. Because again, what we're doing whenever we write all these matrices and whatnot, what we're ultimately going to be doing is writing equations of equilibrium over and over again. Okay? So it's like whenever you did this in statics, like how did we write a sum of forces in the x direction is 0? Well, what we do is we said that's positive, right? And then we had to say something and then start writing everything. Well, it's the same idea here, okay? So we do need to adopt a consistent sign convention. So we're going to say that forces to the right are positive, and we're going to say tensile forces are positive. The stuff going up and down and the rotations isn't going to matter for a bar analysis, so you can sort of ignore this y direction and this theta direction for us right now. It's not really going to matter. Okay. Hi. What's up? It's perfect timing. It's perfect timing. Okay. All right. So I want to look at my one-dimensional bar element, and I want to look at it as follows. Okay? So what I'm drawing here is what I've got here on the board is I've got just a single bar, and what I'm doing is I'm putting the node labels like up here. Like in a model, you'd put them like right there, but it's going to get kind of cluttered right there, so I just stuck them a little higher. And so we'll say some bar of some length L, and we'll say that EA is constant, okay? All right. Now, recall that forces and displacements to the right are positive. So what I'm going to say for this bar is that this bar is going to have some unknown force on each node, right, which we'll say a force going to the right is positive. And then after the structure is analyzed, it's going to respond by deforming some amount. And I'm just drawing them in their positive directions, okay? So we'll say that each joint has an unknown force and a resulting unknown displacement, okay? Does that make sense? And then what we need to do is derive this. We want to derive the stiffness matrix for the element. Okay, that's what we want to derive. So here's how we're going to do this. Okay, a textbook will call this the direct stiffness method, and so the direct stiffness method is basically taking the bar and literally stretching it or squishing it and recording the deflection, or sorry, recording the forces necessary to produce those deformations. Okay, and that's exactly what we're going to do. Okay, so now let's remember that we can compare forces and displacements for a bar with this. Okay, this is what we can use. Okay, and what I'm saying here is that this is for a bar element. If I had a spring, I would just replace EA over L with the spring constant K. Okay, so there's not really anything different there. Sound good? Okay, so here's how I'm going to do this. I'm going to start off with case 1, and I'm going to consider the bar in tension. Okay, so what does a bar look like when it's in tension? If I have bar, and then here's the undeformed bar, and I want to put the bar in tension, what do I do to the bar? Do I make the bar longer, or do I make the bar shorter? Longer. Okay, with me so far? So, here's the bar. Now watch this. Everybody watch up here. So here's the bar. I'm going to deform the bar. Okay? So the bar is going to have some displacement over here and some displacement over here. Now, if the bar is in tension, can somebody tell me what's got to be true as the comparison between these? Delta 2 has to be bigger. That's exactly right. Delta 2's got to be bigger than delta 1. So if the bar was in compression, it'd be the inverse, right? It'd be the flip side. What if delta 1 was equal to delta 2? What would that mean? The bar is just moving, and the force inside the bar would be 0. Does that make sense? Everybody okay with that? Okay. So this is if delta 2 is bigger than delta 1. Okay. So I propose that the total amount of stretch in the bar is the difference between them. Like, think about it like this. If this joint moves over 5 inches, and this joint moves over 2 inches, the total stretch in the bar is 3 inches, right? Because 2 of those is just whoop, the translation, and then there's the other 3 where it got longer. Does that make sense? Sound good? Now, let me ask you a question. If I want to take a bar and stretch it, how do I apply the forces necessary to cause stretch? What do I do? Here's the bar in my hands. What do I do to make the bar get longer? What do I do with my hands? Spread them apart. So the forces necessary to cause tension would be this force is going to the left and this force is going to the right. Does that make sense? Okay. Now I'm saying this is negative. Why am I saying this is negative? What's that? Sign convention, right. It's going to the left, right? We said force is going to the right, we're positive. That's going to the left. Okay? So therefore, here's what I'm saying. I'm saying that this force is EA over L times delta. This force, which is negative F, is EA over L times delta, which is negative this. And F2 is the same thing, only it's positive. Is that okay? So what I'm getting is this. Okay, so I'm actually going to write this on the board. I think I'm going to write it a little less cluttered, and I'm going to say F1 is K, and then F2 is K. But what makes F2 is that the sign convention is, or the subtraction's just a different order. Does that make sense? Here's the awesome part though, is this is if the bar is in tension. What if the bar is in compression? Well, if the bar is in compression, we would sort of do the same thing. We'd say, okay, let's displace. Let's observe our displacements, but then we would find the flip side. We would find that delta 1 has to be bigger, right? So the amount of stretch, or in this case it wouldn't be stretch, it would be squish, right? The squish would be, the subtraction would be reversed, and then I'd go through the same exercise. I'd say this force has got to go to the right, this force has got to go to the left, but here's the crazy part. So watch this. So what I would do is I would write the equations, but look what happens to F1. F1 is the stiffness times delta 1 minus delta 2. Then F2 is the stiffness times delta 1 minus delta 2, but it's negative. So I could just flip the sign and I get the same equations. Exact same equations as before. Does that make sense? So, and by the way, so this set of equations right here, this works if the element is in tension. This works if the element is in compression. Does it work if the element has no force in it? Well, if it has no force in it, then these two are the same. This times this, if these two are the same, then that difference is 0, that's 0. Same thing here, right? Does that make sense? So the only thing left to do is, let's expand these. So what would I get here? I'd get F1 equals K delta 1 minus K delta 2, right? Then what would I get down here? I'd get F2 is, okay, so I'd get K delta 2 minus K delta 1. So if I keep everything in order, I'd get that, right? Is that fair? Just because it'd be K delta 2 minus K delta 1, so I'm just switching them so that everything's lined up. And if I write this in matrix notation, I get the forces equals some matrix times the displacements. And what do I get? What goes here? K minus K minus K, K. Does that make sense? You see what I did there? Just wrote that in matrix notation. So really, the stiffness matrix is just K minus K minus K, K. Or if I want to factor the K out, I get this. And if you're wondering, that's exactly what I have here on this next slide. So what do I have here on this next slide? I say, okay, let's take these equations, expand them, write them in matrix notation, write them in matrix notation. There's my stiffness matrix, okay? The only thing that's different is that if it's a spring, it's K, and if it's a bar, instead of K, it's EA over L. Does that make sense? Okay. If you understand that, then let's talk about how to actually do these problems, okay? So, part one. What is part one? Right here. Assemble the K matrix, okay? So what we're going to do is we're going to write one of these spring matrices for each element in the system, and then we're going to perform this process called assembly. And the best way of explaining assembly is to just show you, and that's what I'm going to do. And basically, all assembly is just putting the stiffness terms where they go in the big system, okay? And once you see how it works, you'll see how easy it is. You'll also see how Excel works miracles for doing assembly, okay? But assembly, if you're wanting a definition, it refers to combining the element level stiffness terms into a global stiffness matrix. And so what I'll do for my notation, again, anytime I got a small letter, small letters correspond to the individual matrices, big letters correspond to the whole system. We then assemble the F vector for the structure. And again, the F vector can be done by observation. And then there's going to be unknowns in the restrained degrees of freedom. And maybe I'll show you a little bit of that today. I want to get through this because I kind of want to look at our problem. We solve for the displacements. We're not going to get to all this today, but we solve for the displacements. And I want to show you how this works when we actually look at a problem. But essentially what we're going to do is we're going to take the big old K matrix and the big old F vector and we're going to reduce it a bit So this term KR and FR stands for reduced. And basically what we do is we reduce it based on the boundary conditions, where the supports are. We get a smaller system, and then we solve. And the beauty about this method, just solve it in Excel. Last thing we got to do is compute the final results. And again, everything that you see here is, I'm just verbatim right here on the handout. But what we're going to do for the results is we're going to compute the reactions, then we're going to compute the element forces. The way that we compute the reactions is we just take the big old K times the big old delta again. And so we sort of recompute F. And if you recompute F, you should get the same answer as before, but where you had unknown terms before, now you're going to have reactions. For the forces in each member, just write a little delta vector for each member. You got a spring matrix for each member, just F equals K delta. And again, this is a wonderful thing to do in Excel because copy paste. Here's what I want to do. I want to spend the next at least few minutes looking at our bar element example. Let me end this. And let's see if we can at least make a little bit of headway on this. Like I said, I'm not in any hurry, but I want to at least take a look at this problem. Okay, so I have a structure, which by the way is indeterminate. Okay, if you look at the forces in the x direction, you have two reactions, but only one equation of equilibrium. So it is indeterminate. Okay, and I want to see if we can solve this using matrix analysis. Okay, so a couple observations. Okay, before we actually start jumping into this. The little spring matrix, the little K matrix, will be 2 by 2 for each element, but then K for the whole system will be 4 by 4. So in other words, there's 1 degree of freedom for each node, so it'll be 4 by 4. Does that make sense? Okay. And then maybe another thing I should say is that F will be 4 by 1. Okay. All right, let me see if I can make a couple calculations and then we'll call it. Okay, so let's look at element 1. So we'll say part 1. Here, let's do it like this. And we'll stop after this because we're going to run out of time. Okay. So element 1. So the first thing I'm going to do is I'm going to compute EA over L. And one of the things that you will find when I do matrix analysis is I almost sort of make it a point at the beginning to make sure that I'm consistent with units. And then I stop worrying about it from then on. Okay, is everybody okay with that? That for element 1, EA over L is going to be 2,000 times 6 over 120 because it's in inches. So that's going to be 100. So here's what I'm going to do. I'm going to say that this is my spring matrix for element 1. Does that make sense? Now, I'm going to show you a taste of how assembly works. Oh. and then we're going to call it. Okay. So these red numbers that I put in front of the spring matrix, see how it says 1, 2, 1, 2? Where do you think I got the 1, 2, 1, 2? It's like this, right? Maybe what I should do is I should say N1, N1, N1. Does that make sense? So would you agree that if I were to try and put these terms where they would go, in how big was the big matrix? So would you agree with this? Then I'm going to use gray. Would that make sense? In other words, like this term goes here, this term goes here, this term goes here, this term goes here, and everywhere else it's 0. In other words, like what this is basically saying is that this bar is not connected over here. So it's not contributing to the stiffness of the system over there, right? What I'm saying is that we're going to do this for element 2, do this for element 3, and then we'll add these up, and that's assembly. Okay? And one final thing. The force vector, and we'll go through this in more detail. Here's what the force vector is going to look like for the whole system. It's going to look like this. The force on joint 1 is unknown. Then it's positive 300, minus 125, and then unknown. How am I getting that? Unknown force, positive, negative, unknown. And why am I calling them R's? They're the reactions. So remember how I said part 2 you could do by observation? It is by observation. Okay, we'll do that more formally on Wednesday, but that's all I got, everybody. I'm going to pull up the code, but I will see you all on Wednesday. Bring your laptops. We're going to do some of this in Excel. So.